Why did this one particular day have more than twice the number of orders over the next most popular day? And has this company got better or worse at predicting the estimated delivery date for orders? We're going to analyse some real e-commerce sales data to answer these questions and more. We will use this dataset here called Brazilian e-commerce public dataset by OList on the Kaggle.com website. You can find a link to this dataset in the description. To download it, click the big download button on the page here. You'll need to be signed in to the Kaggle website first, so create an account and sign in if you haven't already. Save the file somewhere on your computer. This is a zip file, so we'll have to extract it before we can import it. So extract it on your computer. We now have our folder with many CSV files here. Let's import them. For this video, we'll use dbeaver and a Postgres database, but you can use whatever database and editor that you like. We're going to import all of the CSV files into our database. I've got videos on how to do this in other editors and databases, which I've linked in the description. First, we'll create a new database. Right-click on the database entry on the left and select Create New Database. Give it a name, such as OList. Select the owner as the current logged-in user and click OK. The database is created. Right-click on it and select it as the default to make our queries easier to write. Now we can import our CSV files. We have 9 CSV files in this dataset, and we'll import all of them. I'm going to go through this import process quickly as I have other videos on how to import CSV files. To import a file, expand the OList database, then Schemas. Right-click on the schema called Public and select Import Data. The data transfer window is opened. Click Next. I'll browse to the first file to load and select it, then click Next. On the table mapping page, I'll click Next again. On the data load settings page, I'll click Next as well. On the confirm screen, I'll click the Proceed button. The data load will start. After a few seconds, it should be complete. The new table is created and the details of the table are shown here. Click X to close this tab. I'll repeat the import process with the other files, so we'll skip ahead to when this data is already imported. There was one change I had to make during the import. The reviews dataset had problems importing because some of the reviews were split over multiple lines. The easiest fix for that was for me to manually edit the CSV file to replace the new lines with spaces. We can see several tables here, one for each imported file. Our data is now imported. Let's run some simple queries on these tables to see what's inside. We'll start with some simple select star queries. The first table we'll look at is the customer dataset. According to Kaggle, this dataset has information about the customer and its location. We can select all from this table and see what's included. We run this and it shows the data in the table. We have a couple of unique IDs here, a zip code prefix, a city and a state. This is a Brazilian e-commerce company, so the cities and states are not that familiar to me, but I think that's a good thing as it means I won't make assumptions about the data. I'm not sure what the difference between these two IDs is, so we'll have to look into that later. On the Kaggle page, there's a diagram here that shows how each of the tables relate to each other. This will be helpful as we work through our analysis. Also, there are some descriptions for each of the columns here. It kind of explains the difference between the two customer IDs as well. Let's look at the next table. The description of the geolocation file says it has information about Brazilian zip codes and their latitude and longitude coordinates. We can query this table and see there is a zip code prefix, latitude, longitude, city and state. Some of these columns represent the same thing as the first table, but that's okay, as we don't necessarily need the data to be normalized. The next table is for the order items, which are the items purchased with each order. We can query this table and see the data here. We have an order ID, an order item ID, a product ID, a seller ID, a shipping limit date, a price and a freight value. The Kaggle page shows some definitions that we may need to come back to. The order payments file includes information about order payments for a customer. We can see a few columns in this table as well, such as the order ID, a payment sequential value, the payment type, the number of installments, and the payment value. The order reviews file includes information from reviews that the customer has left about the product. In this table, we have a couple of ID fields, a review score, a title and message for the reviews, a review created date, and a review answer timestamp. That seems to indicate a review has an answer. Now the orders file. This is the main table in the database, and it contains rows for each order in the store. In this table, we have a couple of ID fields, an order status, and several timestamps. They may represent different points in the fulfillment process, so there may be some calculations we can do on these. The products table shows all of the products sold by the company. The data includes an ID, a category name, the length of characters from the name and description, the number of photos, the weight of the product, and the dimensions of the product in separate length, height, and width columns. It's interesting that it doesn't have the name of the product, just the number of characters in the name. Next, the sellers table represents the sellers that fulfilled orders for the company. In the database, we can see the seller ID, zip code prefix, the city, and state. Not a lot about the seller in this table. The final table is for category name translation, and it translates the product category name from Portuguese to English. In the database, we can see two columns, one for the name in Portuguese and the other in English. So that's a quick summary of what's in each table. Let's start by finding out a bit more about our customers. What was in the customers table again? We can see some ID values and some location details. I wonder how many customers are in each city and state. Let's write a query for that. We'll select the city and state and then use the count function to find the number of records for each combination. I'll give the count a column alias so it's a little more readable. We select from this customers table. Now, because we're using aggregate functions and non-aggregate columns, we need to add a group by clause. So we group by both the customer city and customer state. Let's order the results by the most popular cities and states, so we order by count in descending order. This query is now ready. Let's run it. We can see a list of cities, states, and the number of customers in each. Sao Paulo is the most popular city for our customers by far, then Rio de Janeiro. So that answers our first question. If you want to get all of the SQL queries mentioned in this video and an entity relationship diagram for the database, get your free guide to this project by checking out the link in the description. Let's look at some of our orders. We can query our orders table to see what we have for each order. We have a few tables about orders, including the order itself, the order items, reviews, and payments. But we'll just look at the orders table for now. We can see some IDs, the status, and a range of timestamps which represent the time and date that the order got to specific stages. Let's start by finding out the number of orders placed each day, so we can get an idea of the volume of orders. How many do we have in this table? We can write a select count on this table. We can run this and see there are 99,441 orders. That's good to know. How many orders are there each day? We can adjust our query to show the order purchase timestamp column, which represents when the order was placed. We can add that to our select clause. We can leave the count function here and then add this to our group by clause. Let's run this query. We can see our results, which show the date and time and the count. Most of the count values seem to be 1. Oh, I see what has happened. The query is showing the order purchase timestamp, but it has a count of 1 for each row because it's the number of orders for that date and time, all the way down to the second. So the only way we will get a count of more than 1 is if there were 2 orders for the exact same second. We want to group by date. So how can we do this? We can do this in a couple of ways. We could use the date function on this order purchase timestamp column, or we could cast it to a date by using 2 colons after the column name. If you're on a different vendor, you can use an appropriate function to convert it to just the date component without the time. I'll use the cast method, so add 2 colons and then the data type of date. I'll do this to the column in both the select clause and the group by clause. Now I'll run the query again. We can see the date values here, without the time, which is what we want. We also see the count of records for that date, which looks better. The dates aren't in any specific order, so let's change that. We can add an order by and then order by the order purchase field. We can see a list of dates in the right order and then the number of orders. We can have a quick look at the numbers and see that they have 100 or 200 orders per day, increasing as the time goes on. So that's question 2 answered. What if we wanted to know what the most popular days were? We can use the same query as we just saw, but change the order to order by the count in descending order. We run this and see our results here. Interesting. The top result is the 24th of November 2017, which has 1,176 orders. It's more than double the next date, which is the day after with 499 orders. The next few dates are all surrounding that date, so the top 5 dates are all in consecutive days. Why is this? What happened on those dates? Was it the same in other years? Further down the list, it shows a mix of dates in different months. There doesn't seem to be a pattern there. Let's see if there is a similar pattern or spike around late November for the other years. We can run our earlier query, which ordered by the date, and scroll through the results. So it looks like the earliest date is in September 2016. We can scroll down a little until November, but we don't see any orders. There does seem to be some gaps in the dates, so perhaps there is missing data, or the store was so small they didn't get any orders, or they were offline. We can scroll down to November 2017 and see the spike in our data there. What about 2018? We can keep scrolling, but we get to the end of the data, which is in October 2018. So we don't have any other November periods to check. It looks like the numbers slowly decreased from August, so perhaps the business was closing down, or there is some other reason for the missing data. Could there have been something else that happened at this time of the year? According to this Wikipedia page, there doesn't seem to be anything that may have happened around this date to cause a spike in sales. What day of the week was 24th of November 2017? Oh, hang on, what's this? It says here that the 24th of November was Black Friday, one of the biggest retail shopping days in the world. That would most likely explain the big spike in sales for that period. So that answers that question. We know a bit about the popular days for orders. What about the popular product categories? We don't have a lot of information about the products themselves, but we can tell what their categories are. Let's find out what categories have had the most number of products ordered. We can get the product category names from the product table and join to the order items table based on the product ID. We shouldn't need to join to the orders table because we have the products that were ordered already from the order items table. I'll also show the order ID and order item ID to see a little bit more about the order. We can run this query and see the results here. We see the product ID, the product category name, which is in Portuguese, the order ID, and the order item ID, which seems to be 1. I'll scroll down a little to look through the data. There are a couple of rows here that look very similar. There is the same product ID, the same category, the same order ID, and a different order item ID. Is there duplicate data here? Why is there more than one item ID? Let's look at the other columns in this table. I'll add oi.star to the query to show all columns in this table and run the query again. We can scroll down to the same row we saw earlier, then scroll to the right to see the rest of the columns. Each row has the same values. The seller ID is the same, the price and freight value are the same. The only difference is this order item ID. What does this field mean? On the Kaggle website, for this field, it says sequential number identifying number of items included in the same order. So it seems like each row in the order gets a new number. The table also does not have a quantity field. So perhaps this order has included 3 of the same product. While we may normally see a quantity field in a table like this design has captured them as separate rows. That explains it. The records are not duplicate. Back in our results, we want to see the popular categories for products. So we need to show the product category name and a count of records. What are we counting here? We are counting the rows of products linked to the order lines, and there will be 1 row for each order line. Knowing what we are counting can help us avoid duplicating our count. If we were to join to another table, which may result in 2 records shown for the same order item, then our counts would be higher than expected. For our query, we can just use count star. We remove the other columns and then add a group by clause. We run this query and see our results. There are some rows with a blank category and then counts for each category here. Let's sort this by the count value so we can see what is popular. We can see the categories with the most orders. This is what we wanted. The values are in Portuguese, but that's okay, we've found the most common categories. There is actually a table that translates the category names from Portuguese to English. We can join to that and then show the English name instead of the Portuguese name. We can do that and then run the query. The numbers are the same, but the category names are different. We can see the top categories are bed bath beauty, health beauty, and sports leisure. So that's our question answered. Let's look at some more complex queries. Earlier, when we looked at the orders table, we saw some date columns. Let's have a look at those again. We have an order purchase, which was when the order was placed. We have order approved, which I assume happens shortly after it was placed. We then have an order delivered carrier date, which is the date the items were provided to the carrier or delivery company for delivery. Then we have the order delivered customer date, which is when the order was finally delivered to the customer. We also have an order estimated delivery date, which was calculated and provided to the customer when they made the order. Is there something we can find out about these dates? We have the estimated delivery date and the actual delivery date. Could we find out how close the estimate and actual are and if they have gotten better or worse over time? Let's say we want to see this difference for each month. So the average difference between these two dates to see how it changes. Sounds complex. Let's start with something small. We'll write a select query to show some information for the order. Just the delivery date and the estimated delivery date. We don't need any of the other dates. We can see our results here. Most of the orders have both dates populated, but there are some that don't. We can see that the orders with a status of delivered have a delivered date, and other statuses, such as shipped or invoiced, don't have this date. The delivered orders are the only orders we are interested in, so let's filter on those. We run this query and see the results. Now let's calculate the difference between the two dates. In Postgres, we can do this with a simple subtraction. We subtract the delivered customer date from the estimated delivery date. This should give us a positive number if the estimate is greater than the actual delivery date, meaning the delivery was earlier than estimated. I'll add a column alias so we can better understand the column in the results. Let's run the query. We run it, but we get an error. It says operator does not exist, character varying minus character varying. This means we are attempting to subtract a value which is character varying data type, which is a kind of text value, from another character varying value. But these are timestamps, aren't they? Let's see what data type they are in the table. We can expand the database on the left, then the orders table, then columns. We can see all of the columns and data types here. It shows our date columns, but they are actually a varchar data type. That data type was set when we imported the data. So that's why the error has occurred. Fortunately, we have a way around this. We could alter the table to change the data type, but for this example, I'll convert the data type in the query by casting it to a timestamp data type. In Postgres, I can add 2 colons after the column name, then add the word timestamp. This will cause Postgres to convert the data type to a timestamp within our query. I'll add this to both of the individual columns, as well as the columns that we are subtracting here. Let's run this query. We see some results and don't see an error. We can see the column headings of our 2 dates here that have this little clock icon, meaning it's a type of date. Earlier, this showed an ABC value, like the order status column does here. We also have a new column called date diff. This is the difference between our 2 dates. It's shown as an interval data type, which is a representation of time of the difference between the 2 dates. This is helpful as it's quite readable. We can see the number of days, hours, minutes, and seconds between the 2 dates. This first order has a difference of 7 days. It was estimated to be delivered at midnight on the 18th, but it was actually delivered late at night on the 10th, which is a little over 7 days. We've got the difference for each order. We want to find the average for each month. Let's calculate that now. What do we mean by month though? Is it the month of delivery, or the month the order was placed, or something else? Let's say we want to base it on the month the order was placed, which in our table is the order purchase timestamp column. First, we add that to our query. We run this and see our purchase date column. Now we want to find the data for each month, so we need to convert this to a month. We can do this using a function called datePart, where we specify the value of month and then this purchase date column. We can see the column here called order month, which has a number representing the month. This is only the month of the year. We don't have the year. We want to group by values such as October 2017, November 2017, and so on, not by all October orders or all November orders. So we'll need to get the year. We can use the datePart function again, but this time getting the year. We'll add it as a new column as we want to see both the year and the month. We run this and see the results, which show the year and month of the order. We're making progress. We've got the month and year. Now we need to see the average per month and year. So we want to show the year, month, and then the average of this date difference value. We'll update our query to remove the order ID and order status columns. We also don't need to show the individual dates here. Then we surround this subtraction calculation here with an average function. Finally, we add a group by to the query, specifying the order month and order year. We are able to use column aliases here. We run this, but we get an error. It says invalid input syntax for type timestamp, then an empty string. What does this mean, and why are we only seeing it now? For some reason, this query is showing an error because there is a timestamp that has a value of an empty string. But we filtered out the records that were not delivered, so I'm not sure why this is happening. Let's query the orders table to find rows where either of our two columns have an empty string, the estimated delivery date or the customer delivered date. We still only want to see values that have a status of delivered, so we include that in our where clause. We surround the two date checks in brackets as we want rows where either of those conditions are true. We run the query and see a few rows here. Interesting. We have 8 rows here that have a status of delivered, but they have a missing order delivered customer date. The order purchase date values are all different, so it doesn't seem related to a specific date. So I believe that error we saw earlier was happening because we tried to perform a calculation on an empty timestamp value. We only saw it on our query with the grouping because we probably didn't fetch these specific orders from the database yet. So what do? We should exclude these records from our query. We can update our earlier query to exclude records that have an empty customer delivered date. Once we do that, we can run the query. We can see our results here. We see a year and month, and then the average date difference. Looks good so far, and there were no errors. The dates are not in any order. Let's order it by year and then month. We run this and the data looks a little easier to understand. We can scroll down and see how the data has changed. It looks like it starts around the 20 to 30 days mark, and then over time it gets down to about 7 to 12 days. Now, because we said estimated delivery date minus actual delivery date, this is the number of days that the estimate is after the actual. So the number means the average number of days that the actual delivery date was earlier than the estimated delivery date. If we look closely, we can see some strange values in the date difference column. The second row here has a value of 35 days and 25 hours. There are only 24 hours in a day, so that doesn't make sense. Many of the others are okay, but we also see a value of 10 days 27 hours for 2017 October. What has happened here? Well, the calculation is correct, but it seems like the extra hours have not been converted into days. This is the way the calculations happen with intervals in Postgres. It doesn't always flow the extra values into the higher unit of measurement, like hours into days. Fortunately, there's an easy way to fix this, and it's to use a function called justifyInterval. This will round all components of the interval to the right unit of measurement. We can surround our average function with justifyInterval. That's all we need to do. Let's run the query again. We can see the values are updated. That first record we saw with 35 days now has a component for months, and the hours have been reduced. We can see that all of the hour values have been reduced as well. So our data looks pretty good here. We could display this data as a chart to understand it a little better, but we have the data to answer our question. If you want to get all of the SQL queries mentioned in this video and an entity relationship diagram for the database, get your free guide to this project by checking out the link in the description. We've calculated the average difference between expected and actual delivery dates for each month. Let's say we are looking to improve our delivery process and we want to find orders that took longer than normal. We want to see the orders that have a difference between the expected and actual delivery date, which is higher than the average for the month. Let's start with seeing the details of the orders again, like we did earlier. We'll see the order ID, the two delivery dates cast to timestamps, and then the difference between the delivery dates. So we've got the difference for each order. How do we tell if it's higher or lower than the average for the month? We need to calculate the average for the month. Now, the average function is an aggregate function. We want to see the details of orders. If we want to see the details of rows as well as the results of an aggregate function, we can use the aggregate function as a window function. I'll show you how we do that. If you want to see more about window functions, you can watch this video here. We start with the average function, and it will be the average of these two dates subtracted. After the brackets, we add the word over to define this as an aggregate function. After over, we add brackets. Inside the brackets, we can define our partition, which is a group of rows to perform this average function on. How do we want to calculate the average? Well, it's the average for all orders in that month and year. So we partition by the order month and the order year. We calculated those earlier using the datepart function, so we add those in here. I've separated this over clause onto separate lines to make it easier to read. If you're thinking this is a lot of code, then I have a way to clean it up, which I'll show you soon. We give it a column alias and then our query is ready. We can run it and see our results here. The new column shows the average difference for the month. We have some orders here which were ordered in the same month, and they have the same difference value here. We can scroll down and see orders in the next month which have a different average. So this is good. We've got the average for each month. How can we use this to find orders that are later than the average? We can filter our orders to show rows where the date diff value for that order is less than the average for the month. The number represents the number of days the order was delivered before the estimate. So if the difference for the order is lower than the average, it was delivered later than average. So we update our where clause to filter on this. We run this, but we see an error. It says the date diff column does not exist. It happens because we can't use column aliases in the where clause. One way to resolve this is to add the full calculation into the where clause like this. We'll have to do this for both columns. We try this, but we get another error about window functions. Well, now we have errors and our code is messy. There is a better way to do this. We've got a bunch of calculations in our query. One way to improve this is to use a subquery. We have a subquery that selects the values we want to work with and then gives them column aliases. Our outer query can then refer to these column aliases, making our query simpler. Let's try this. We have our order ID, the calculations for the order year and month, the actual delivery date as a timestamp, and the estimated delivery date as a timestamp. We run this query and see some results. We've gone backwards a bit, but that's okay. We'll add our subquery now. We select each of our columns using the aliases here. We can also calculate the date difference by just referring to these two columns. We don't need the original column names or the cast to timestamp, as that has already been done. Then we add the from clause and surround this query in brackets. We add an alias to the subquery as that's a requirement. Let's run the query. We can see our results here, which include the date difference. Now let's add the average for the month. We can use the same average function as before, but the parameters are much simpler because we can use the column aliases. We run this and see our results, which include the average difference for the month. Finally, let's try to filter. Now, we can't filter on window functions, so we can't just add this average function to the where clause. But we have given it a column alias, so we could surround our entire query in another subquery. We can do this, and then add a where clause to check whether the date diff is less than the average month diff. We can see our results here. We only see orders where this date diff is less than the average for the month. These are the orders that were delivered later than average. So that's our question answered. We've used a range of SQL features in this data analysis, from simple selecting and grouping to multiple subqueries with window functions and aliases. You'll want to watch this video next, which is another example of performing data analysis in SQL on a car sales database. Thanks for watching.